Welcome to the course on Polymeric Biomaterials, and today's lecture we are going to be focusing on the definition of mer, monomer, oligomer and polymer. So in the last lecture we looked at concepts related to polymeric biomaterials in general, and we saw the importance of structure property relationships, and from this lecture onwards we will now be looking at understanding some of those structures, understanding how structures can be thought of at multiple length scales and how that leads to specific types of properties for polymers. So in that spirit, today's lecture we will be looking at some definitions that are important for us to understand. We will first begin with what is typically called the macromolecular hypothesis, which is essentially how polymers came to be discovered, and then we will contrast polymers with small molecules that we are typically familiar with, just to understand the differences in properties between polymers and some of these small molecules. And then we will specifically look at some unique features of polymers that make them distinctively different from small molecules, and then we will discuss the definitions of mer, monomer, oligomer and of course polymer, and then end with looking at a discussion on the importance of polymeric structure. So we can first start by asking a very broad general question: what is a polymer? What is considered a polymer, and how did this first start? So largely the idea of a macromolecule or a polymer comes to us from Staudinger, who for the first time hypothesized or postulated that what he was making in the lab was a sequence of molecules that were covalently bonded, and these individual units were called monomers. Now, what is important to understand here is two things. One is, you have short repeating molecular units leading to a large macromolecule, and these repeating units are linked by covalent bonds. Now contrast this with another theory that was floating around at that point, which is for the same material that was synthesized in the lab, there were other scientists who were postulating that this could not be covalently bonded, and because that was a very hard idea for them to accept at that point. The argument was that what you are really seeing there is an aggregation of molecules leading to a colloid-like structure. So that is called the aggregated colloid hypothesis, where lots of small molecules could aggregate and form colloids. That is one theory. Of course, the theory that put forward by Staudinger was that you have these molecules linked together in a long chain by covalent bonds, and it is simply not aggregating together. That is not what is happening. It is very interesting history, and if you get a chance, please look it up, and for this Staudinger won the Nobel in 1953. Now, we have already seen that a polymer, you can think of it as a long chain molecule with a large number of repeated subunits. So again, there are 2-3 important ideas to note here. One is, it is a long chain molecule. Second is, it is composed of a large number of subunits. Third, the subunits repeat. So all three of those are important. And of course, we will be looking at multiple examples of the structure and so on in this lecture. One consequence of a large covalently bonded set of molecules resulting in a long chain leads to very large molar mass. That is why it is called a macromolecule. large chain length and a long chain length and a large molar mass, as opposed to say a salt, for example, which is a small molecule. So let's dwell on that question a bit more and ask how is a polymer different from a small molecule, and we will take the example of polyglycolide, which we have seen in an earlier lecture. If you remember, it's a biomedically important polymer because it's used as it's a fairly crystalline polymer and it's used for orthopedic fixation screws. That's the use primarily, and it's degradable. It's a thermoplastic, highly crystalline polyester. All of these words will mean something as we go through the course, but again, for now, just note that it's a thermoplastic, it's crystalline, and that in turn will have specific implications, and it's a polyester, which has something to do with the chemistry. So the thermoplasticity has to do with both the structure and the mechanical properties. The crystallinity has to do with the microstructure, and the fact that it's a polyester is something to do with the chemistry of the polymer itself. Now, if you think of properties of this polymer, firstly you will realize that you will only see ranges in the literature. You will very rarely see exact values, and that is one thing that we will have to sort of get used to very quickly with polymers. Why this happens we will see in more detail, but for now it's important to appreciate that depending on how the polymer is synthesized, how long the chains are all the chains in the polymer the same length, all of these things will go to determine what the actual properties will be. You can also have cross-linking between the chains. The chain can be one long chain or it can have multiple branches. So all of these factors will go into determining the actual properties. So typically you will see ranges of properties, and that's one key distinction for polymers. This is true even for mechanical properties, for example. You will see a range. The other thing is, I am mentioning two specific properties here. One is a melting temperature, the other is a glass transition temperature. Again, why don't you search a little bit right now to get a sense of what these terms mean. We will do a far more detailed formal analysis in due course, but it might help if you do a quick search to understand what glass transition temperature actually means for PGA. So as you heat this polymer, it's going to soften first, which means it's going to take a hit on the mechanical properties. And once it reaches its melting point, you're going to get a viscous melt thereafter. So you've gone from something that was more solid-like to something that has melted beyond its melting point, and thereafter you don't get, if you keep heating it further, you don't get PGA vapor. That never happens. Unlike a small molecule, for example, like N-hexane, which melts at minus 95 degrees centigrade and boils at 68.7 degrees centigrade. Notice that both of these are exact numbers, not ranges, and you actually get the vapor once you heat it beyond a certain point. That will never happen in a polymer. You will get a viscous melt, and if you heat it further, what you will get is another event called decomposition. So very broadly, you see that that's one way to contrast polymers from a small molecule, which is also a hydrocarbon, by the way. A lot of the polymers we will see in this course are hydrocarbons. So that's why I am taking the example of N-hexane, which is also a hydrocarbon, but you see the properties are very, very different, right? So that's one level at which we can initially start appreciating how polymers are different and why are they unique. So at this point, it might be a good idea for you to pause and reflect on two things. One is, you are talking about a large molar mass and very long chains, and you are talking about property averages or ranges in properties, and that, like I said, is a consequence of how the polymer is processed, what its structure is, how long the chains are, what is the distribution of chain lengths, what is the bonding between the chains, Are there cross links that exist? Is there branching in the chains? How tightly are the chains packed? All of these will play a role in determining the actual properties. So, dwelling further on why polymers are special, when you have long chains, you end up getting what we call molecular entanglement. Now, the typical picture that is given is that of a bowl of spaghetti, cooked spaghetti if you will, or noodles, and if you have chains there, if you think of those as polymeric chains, you see that the spaghetti chains are all entangled, right. So, that is one picture that you can have to begin with when you think of polymer chains and molecular entanglement. You see the same thing when you look at cooked noodles or cooked spaghetti. You see intertwining, you see entanglement of the different chains. You can also have intermolecular interactions, and this can again be thought of at different length scales. You can start with molecular level, where we are talking about how the different units are connected to each other, and as we saw, that is covalent bonds that connect the different units together in a single chain. And then you can have interchain interactions, right, where two different chains can now interact based on what the chemistry is, using what are called secondary interactions. So, these can involve non-covalent interactions sometimes, like hydrogen bonding or van der Waals forces and so on, through which chains across within the polymeric system can interact. And then you can talk about how chains can also organize. If you have cross-linking and so on, you can get at a slightly bigger level, you can get a 3D network of chains, and that will have its own unique properties. So, that is one thing that makes polymers special, because you are talking about hierarchy in organization, and this is more commonly seen, this hierarchy is very beautifully seen in natural polymers like proteins, where you have different orders of structures. If you have some bio background, you might be familiar with primary, secondary, tertiary and quaternary structures of proteins, and those can be thought of as involving different types of interactions at different length scales, leading to higher order structures. That is a very important theme in polymers in general, but more so very clearly, very beautifully observed in natural polymers like proteins. Collagen is another polymer protein that we have seen earlier, where we have seen specific types of hierarchy earlier very briefly. You can also have silk, which we have alluded to earlier again, and one reason why silk gets its exceptional mechanical properties is because of how it is organized in terms of its structure, which we will look at later. But the point I am trying to make here is this hierarchical organization and self-assembly for natural polymers, for example, and for synthetic polymers, looking at interactions at different length scales can give you a sense of how properties can emerge at the bulk. You also have diversity in structure and properties, and this is something we have seen earlier. Polymers is a very broad term for a series of different types of materials which can exhibit a wide variety of properties. Not only that, the same polymer can exhibit different properties depending upon microstructure, processing and so on, depending on chain length, depending on molecular weight, molar mass, all these things. And that in turn determines how diverse the functions and applications of polymers are. So, just as an example, we have seen some of these things earlier. You can think of a hip implant liner, you can think of dental resin, you can think of a knee filler, you can think of a dialysis fistula. One is an orthopedic application, actually both of these are. Then this one is a hyaluronic acid, for example, is used in patients to lubricate the knee for patients who are suffering from osteoarthritis. And that's a viscoelastic filler that lubricates, that provides lubrication that has been lost due to the onset of osteoarthritis. And then you can talk about a dialysis fistula for a vascular access graft made out of PTFE. Now you see right here in just these 4 examples, you see the range of properties that will be required from the polymer. The demands are extremely different. The application is extremely different, and in yet polymers can be used for all of those, except that they have to be chosen correctly with the right kind of properties. First thing is, when you dissolve a small molecule in a solvent, talk about mole fractions, because the solute molecules don't take up appreciable volumes. But remember, polymers are macromolecules. The word macro itself should tell you something, that they will take up appreciable space, 3-dimensional space, which means you are now going to talk about volume fractions, and that's something we will use in this course to understand how polymeric solutions are prepared, and we later talk about the Flory-Huggins theory. Another important unique aspect of polymers when it comes to solvent interactions is when you try to dissolve some of these polymers in solvents, and if the polymer can be dissolved in the solvent, it's not an immediate quick process. There is first solvent induced swelling followed by complete dissolution. The solvent has to penetrate, and then there is swelling, and then complete dissolution happens over time. The third thing is, viscosity effects are both functions of solvent and temperature. So these polymers in solution, for example, can exhibit different viscosities based on their volume fraction. And that is true as well in the melt state, where you can take a polymer, melt it, and depending on the temperature, the viscosity can be different. This is a very interesting dilemma in polymers, which is, on the one hand, you want processability, and on the other hand, you want good mechanical properties. As you will see later, if you have very long chains, very high molar mass, mechanical properties can go up, but that reduces the processability, and vice versa. So this is an interesting challenge for designing polymeric biomaterials for specific applications, where you want to process them into interesting structures or useful structures, biomimicry for example. Right? If you want to make biomimetic structures, you want them to be processable, but if they are super easily processable, it's very likely that they will not be very good when it comes to mechanical properties. And where that matters here, for example, is we will later look at a process called electrospinning, which is a fiber spinning process using electric fields, and their polymer entanglements have a direct impact on the formation of fibers, which can be used to form these non-woven meshes that we looked at earlier, which architecturally mimic the extracellular matrix of tissues. So that's where, and you can have both solvent based and melt based electrospinning. So solvent based would be this, melt based would be this, their viscosity becomes important. In polymers, you can also have temperature induced chain motions and transitions depending on what the temperature is. How the solvent interacts with the polymer can also be a function of, can also be tied to temperature. Temperature can also be used to induce transitions in polymers going from hydrophobic to hydrophilic or hydrophilic to hydrophobic. One example of that is polynipam, poly-N-isopropyl acrylamide, which I would encourage you to look up. It has a very unique property that at 32 degrees it undergoes a transition. What kind of a transition does it undergo is something that I would highly encourage you to look up. And like I said earlier, temperature will affect the bulk mechanical properties because if you want to use the polymer at 37 degrees Celsius, then you have to consider that when you design the material, because the mechanical properties will be performing to that extent only when used at 37 degrees. So, your tests have to account for the fact that the polymer will be used both in the presence of a solvent, which is in the case of the body will just an aqueous buffer, which can have its own effects, and the fact that it is going to be used at 37 degrees. And like I said already, solvent and temperature influence processability and performance. So, with that background being set, now we go into defining some keywords that are important for us to understand polymers. First one is the repeat unit, or what we call mer. That is the mer in polymer. Mer here is simply the repeating unit linked together covalently to form a polymer chain, right. So, we talked about polymers as having a repeating unit that repeats continuously in a long chain, and that repeat unit is called a mer. Now, this repeat unit is a chemical entity with a fixed number of atoms. So, the mer itself will have a specific number of fixed atoms, and it will repeat over and over again, and depending on how many mer units are there, the chain length is fixed for a given polymer. And the mer has the ability to form a long chain linked by covalent bonds, and this is something we have already seen. And shown here are two examples of common polymeric biomaterials that are used both in biomedical engineering and in the clinic. On the left you have polyethylene glycol or PEG, and on the right you have polyhydroxyethyl methacrylate or polyhema. Now, this polyethylene glycol is used as, we already seen that it can be used as non-fouling coatings on surfaces. It can also be used as excipients in drug release systems. Whereas polyhema is used in contact lenses. Now, what you see here immediately is two things. One is that this nomenclature that we have here is typical for polymers, where you show the mer repeating unit this way, and then there is a small n as a subscript at the end, which indicates the number of times this mer unit repeats to form that long chain, and that n can be a very large range depending upon how the polymer is made, what polymer it is, and so on. And n here has a formal name, it is called the degree of polymerization. Note that it is the average number of mer units per chain, and it can be anywhere from 300, 400 thereabouts to all the way up to 10,000 or even higher, depending upon the polymer. So, one maybe thing you can do is to look up for ultra high molecular weight polyethylene that we have seen earlier. You already see that ultra high molecular weight should mean something to you, although we have not discussed molecular weight formally. Can you try and see if you can look up what the degree of polymerization could be for ultra high molecular weight polyethylene, and then try to justify why it is called ultra high molecular weight polyethylene. Maybe you can do it as an exercise. It is an interesting exercise to look at. Looking at MERS in more detail, some more features include MERS having either saturation or unsaturation. It can go both ways. MERS need not always be hydrocarbon based, they can be inorganic materials as well, and they can still be polymers. MERS can also have different functional groups. So, shown here are some examples of polymer families based on different MERS, and what you have here is polyglycolic acid, which is organic saturated, and then you have polyisoprene, which is organic but unsaturated, and then you have polydimethyl siloxane, which is inorganic. It is no longer hydrocarbon based, it is silicon and oxygen based in the MER. And then you have polytetrafluoroethylene, which is a fluorinated polymer. So you see, right away we have 4 types of polymers, and all of them in some sense can be used for some kind of biomedical application. We are going from an organic saturated to an organic unsaturated to inorganic to a fluorinated polymer, depending on whether they have saturation or unsaturation in the backbone, whether they have carbon hydrogen based MER, or whether they have functional groups that are specific. And as a final example, you also have the COO minus groups in hyaluronic acid, which would be considered a polyelectrolyte, which is a charged polymer, and that can have specific implications for its functionality wherever it is present, particularly in the cartilage. And as we will see later, charge here plays a very important role in how it interacts with its surroundings, and that plays a very crucial role in how it helps the cartilage do its regular functions in the knee. Now that we have looked at the idea of a MER, which is simply the repeat unit, we now look at what we call the monomer, which is not the same as MER. It is the one part that reacts to form a polymer. So monomer is a complete molecule in itself. For example, here the monomer here is tetrafluoroethylene, which is this, which is a complete molecule by itself, and when it is polymerized, we get a polymer here with N. So earlier when we were looking at monomers or MERs, this N is the number of times it repeats. The MER itself will not have the N. This is simply the MER. The number of times it repeats, when it is added, it becomes the polymer. Whereas here you see that this is a complete molecule in itself, and when you polymerize it, you get a polymer where here in this case it is polytetrafluoroethylene. So at this point, it might be good for you to reflect on the differences between MER and monomer, noting that they are not the same thing. Oftentimes this is a point of confusion, but as you clearly see, this is not the same as this. This one is the MER, just this unit, and then this is the monomer. So I hope the difference is clear. You can also have oligomer, which is a few MERs joined together. So this is sort of an in-between. A monomer is just a single molecule. A polymer has n number of molecules covalently attached, and an oligomer is only a few MERs joined together typically around 2 or 3 to about 20. You will hear this quite often in the context of amino acids which form the monomers for polypeptides or proteins, and there you can have something called a peptide, which is sort of the biological analog of an oligomer, where it is a short chain sequence of amino acids, perhaps 20, which is much smaller than a protein, but still has units of monomers joined together. So, here shown here is an example of one such tripeptide, which is glutathione tripeptide, which is an antioxidant molecule which with scavenging capabilities, which is present in many mammals. And the 3 amino acid sequences that make up this tripeptide are glutamate, cysteine and glycine. So, you have glutamate, cysteine and glycine in that order linked together by covalent bonds to form what we call a tripeptide or an oligomer in a more general sense. So far we have looked at mer, which is simply the repeat unit, monomer, which is the basic unit molecule that reacts to form the polymer, and we have looked at oligomer, which is a few repeat units joined together to form a structure which may have about 2 to 20 kind of repeat units. Now, if you extend that argument, you can now go up to n, which is the degree of polymerization, number of times that this unit repeats to get the full polymeric structure. And as we have already seen, polymeric structure can be discussed at many length scales, where hierarchical organization is critical, especially for biopolymers. And a lot of the bio-inspired, biomimetic approaches that involve self-assembly take advantage of this hierarchical organization and try to exploit that to design materials that show different types of functionality and properties at different length scales. Now, when you think of polymeric structure, one thing that we should think about more carefully is the chain level primary structure, or what happens in one chain of covalently linked mers joined together in one long chain is required for us to understand and appreciate what happens at higher levels of organization. So, we start off with one level below the chain, where we are looking at how the chain in itself is formed. So, there you can talk about the molecular structure, where you can talk about what kind of atoms are sticking out. We saw that you can have different functional groups, right, in the mer. So, based on the mer, what is the molecular structure? That is something you can think about. You can also have these things influence the chain structure itself, and then that forms the link between how individual mers and the groups etc. around them can ultimately have an effect on interchain interactions and how that leads to higher order properties. So, properties such as molar mass, which depends on how long a chain is, molecular architecture, which includes things like whether a polymer chain is linear or is it branched, these kinds of things, and the chemical composition itself. We saw different families of mers. All of these influence the properties of the macroscopic material, right. Therefore, understanding the structure is key to understanding properties. So, we will end by reflecting on this important paradigm in polymeric materials, particularly polymeric biomaterials, where structure dictates properties, structure properties together dictate function, and function dictates performance. And of course, because we are not just using polymers as such, we are processing them and designing biomaterial implants, processing becomes very important, and structure property relationships can be heavily influenced by how the material is processed, which also we will look at in subsequent classes.